This is problem 158 from chapter 12. An airplane is flying in a straight line with a velocity of 200 miles per hour and an acceleration of 3 miles per hour squared if the propeller has a diameter of 6 feet and is rotating at a constant angular rate of 120 radians per second. So the angular rate, that is theta dot, you can tell by the units. Determine the magnitudes of the velocity and the acceleration for a particle located on the tip of the propeller. So we can say this point right here. We want the magnitude of the velocity and the acceleration. We are looking at cylindrical coordinates here, and actually this is the first problem that we see in which we actually do get to use cylindrical coordinates rather than polar coordinates, because it is a three-dimensional problem. So equation 1231 is for the velocity, and equation 1232 is for the acceleration. One thing that's kind of weird in this problem is that they give us the velocity in units of miles per hour, but they give us the angular rate in units of radians per second and the diameter in feet. So we want to either convert the feet and seconds to miles and hours, or convert the miles per hour to feet per second, and the acceleration we would have to convert also. But we're not quite at that point yet. So the first thing that we're going to do is look at what we have in our velocity and acceleration equation and write down some of those values. So I need the radius. This is for a point on the tip of the propeller. The propeller has a diameter of 6 feet, so the radius would be 3 feet. And in my equation for velocity, I have r dot, but the point on the tip of the propeller, that is always staying 3 feet away from the center of the propeller. So r dot is equal to 0. R double dot is equal to 0 because the radius is not changing. Okay, so then let's look at theta dot, which we were told was 120 radians per second. And did it say it was constant? Let's go back and look. Rotating at a constant angular rate, yes. So theta double dot is equal to 0. I don't need z itself, but I do need z dot and z double dot. And z dot and z double dot, similar to what we had in rectangular coordinates, that would just be the velocity in the z direction and the acceleration in the z direction. We're going to say this is the z direction, since this is the radial direction and this is the transverse direction. So z dot is 200 miles per hour, and z double dot is 3 miles per hour squared. But while we're here, let's go ahead and convert the 200 miles per hour to feet per second. So I have to take care of the miles in the numerator and the hours in the denominator. And as you may recall, there are 5,280 feet in 1 mile. So that's going to take care of the miles. So this will cancel out with that. We have hours in the denominator, and there are 3,600 seconds in 1 hour. So that will take care of the hours. Oops, that was the wrong color. And so that gives us 293.33. And that is feet per second. We do something similar for the acceleration, but the difference is that I have hours squared in the denominator. So I multiply in the numerator by 5,280 feet per mile, which takes care of the miles. But since I have hours squared in the denominator, I have to multiply by 3,600 seconds per hour twice. So that would be 3,600 squared. So I have hours squared here, and that would be squared because the whole quantity is squared. And that gives me 0.00122222. And that is now feet per second squared. Okay, so I think we're in good shape now, and we can go ahead and take everything that we have here, plug it into the velocity equation and the acceleration equation, and we should be good. They do want the magnitude of the velocity and the acceleration, but it doesn't hurt to write out the velocity as a vector before finding the magnitude, so let's do that. So we have r dot is equal to 0, so let's just leave that out. We have r, which is 3 feet. I am going to put the units in here because it might be worthwhile, just checking to make sure that everything works out since we did have to convert. So r times theta dot is 120 radians per second. Remember that the units of radians come and go for free, so in this case we don't want the radians because we want the velocity in feet per second, so we can just cross them out. Then we have z dot. Z dot we said is 293.33 feet per second, and that's in the z direction. That looks good, and I can go ahead now and find the magnitude by squaring both components, adding them together, and taking the square root. 3 times 120 is 360, so this is 360 squared plus 293.33 squared, add them together, take the square root, and we get 464. And this was feet per second, this was in feet per second, so that's 464 feet per second for the magnitude of the velocity. Now we can turn our attention to the acceleration. So the first thing that I'm going to do is just use the acceleration vector that I have here and plug in the quantities that I have. So r double dot is equal to 0. Let's just leave that out then and say minus r, which is 3 feet. So this is minus 3 feet times theta dot squared. Theta dot is 120 radians per second. And this is the radial component. The radians, again, we don't want, so we can just cross them out, and then I'll have feet per second squared, so that will be good. Now I have r times theta double dot. Theta double dot is 0, so that first term is 0. I'm not going to write it, but you can if it helps you to keep track of things. Plus 2 times r dot, which is 0, so the whole thing is 0, so there's no transverse component for the acceleration. So I'll just leave that out also. Then I have z double dot, which is 0.001222 feet per second squared, and that is the z component for the acceleration. So this is in feet per second squared, this is in feet per second squared. I can go ahead now and find the magnitude of the acceleration. I need to square both components, and this is 3 feet times 120 radians per second squared. So that would be 43,200. And then I need to square that plus 0.001222. Now take a look at what we have here. We have a large radial component and a very small z component. So when I find the magnitude, this z component is not going to have much of an effect. And so unless you want to use a large number of significant figures, when you do this, you will just get 43,200. So it is actually larger. The magnitude of the acceleration is larger than the radial component, but by a negligible amount. So we have feet per second squared, Or we can write this as 43.2 times 10 to the third feet per second squared, and that is the magnitude of the acceleration.